9.2 says, you know what? We can still use F equals ma even if we have a bunch of particles, as long as we know where the center of mass is of that particle. Okay, so I could have a problem like this and say, we've got, you're not on the board yet, sorry. Give me one sec, guys. I might have lost my screen mirror, and give me a second, but it's still going to work. It is nice. Okay, I got to reset my password. So in 9.2, it says like, hey, you know what? An object is fired, and it's moving, and it's moving, and it's moving, and then suddenly that object explodes. Okay, that object suddenly explodes. How can we follow its trajectory? How can we study it? Well, we can do the following. We can follow its center of mass the rest of the way. Sure, all these other particles are going off in random directions, and they're not random really, but in other directions. But the center of mass of all these particles, as all particles continue to go and spread out further and further as it's falling, the center of mass still follows the trajectory that the center of mass started on. And that's going to go into conservation, or that's going to come from really conservation of momentum, really, we're going to see. So 9.2 is simply saying that, you know what? This is true for a single particle. This is also true if we know that the center of mass is moving. That's COM, center of mass. So 9.2 literally does a whole derivation extending upon why you can use F equals ma for a particle system or for a bunch of particles, provided you know their center of mass. What else? That's pretty much it. I mean, this is still the overall force acting on it. This is, again, 9.2 that I'm talking about. This is still the overall force. So your book does an example where it's got like 3 particles, and each of them have a different force acting on them. Okay, so the forces look like that. Let me put another color so it shows that they're different. So each of the particles has a different force acting on it. And the key to this problem is to simply sum the forces in the x and sum the forces in the y. And then you can get the center of mass somewhere in between and figure out what happens to the center of mass. This is not one of your typical problems. This is, if anything, going to be maybe a multiple choice style problem. It's not going to be a part 2 style problem. But the idea behind it is that you can find all of these because you'd be given the values. Like this would be 2 newtons, maybe this is 3 newtons, this is 1 newton, this is an angle of 15 degrees, this angle here, let's say that's 25 degrees, the other one is acting straight down. So I could sum the forces in the x direction and use max, and sum the force in the y direction and use may. It's no different. It's not going to act any differently. The key is to recognize, though, that we find the center of mass and then behave and understand how the center of mass behaves as a result. So the center of mass might be a dot like, let's see, it's going to be shifting more to the right and slightly down. So probably like right here, I'll put an X. Okay, the X there in the middle of that diagram is what's representing the center of mass. So the center of mass will feel a force in the x direction and the y direction. And here we have to do 2 cosine 25 to go in for this force. This will be 3 cosine 15 to go in for this force. And this would be 0 because this is only in the y direction. And then the sum of the force in the y direction here, this will be 2 sine 25 minus 3 sine 15 because it's acting down and to the right, and then minus 1. Okay, those will give me the sum of the forces. And again, I would still be looking at the center of mass for this problem. And this is going to be, God bless. Oops. It's going to be a minus here because the forces in the y direction are acting downward. And again, there are 3 forces acting in the y direction, but only 2 of them are acting in the x direction. The yellow force is only acting in the y direction in the diagram there. What would the m value be? The m would be the total mass of the system, because we are looking at the acceleration of the center of mass. The acceleration of the center of mass. Your book does a ton with subscripts here, and it gets a bit cumbersome. This says the acceleration in the y direction, comma, for the center of mass. That's what this is saying right here. The acceleration in the x direction for the center of mass. So this m that's listed here is the total mass of the system. Your book uses a capital M to indicate that it's the total mass of the entire system there. So maybe a capital M for these two I'll change so you can see it. Okay, total M. So if you knew the mass was like, 2 kilograms, 1 kilogram, 4 kilograms, with those masses and all these positions, you can find the center of mass, which it really doesn't even matter the center of mass, where it physically is right now. We can figure it out so we know where it's headed. So if we knew the exact position of the center of mass, we could find the position of the system at some future time or at some future location because we know the overall force, and therefore we'd have the accelerations in both cases. Okay? My recommendation for this one is just look at the example. Read through the example on page 223. Okay, 223. I'm going to move on to 9.3, and I'm only moving on for the sake of time right now. I'm realizing more and more that we have to start speeding up if we're going to really get through all the material this year, so I don't want to get to the point at the end of the year. All right, we're stuck now. So again, that was page 223 you want to read. Let's look at 9.3 and 9.4 together. Now, 9.3 and 9.4 have two main overarching themes. The first concept is this. Momentum is conserved. Momentum is conserved. And it's not really introduced until you get to like section 9.5, I think, in your text. But that really does play a role. First, what is momentum? What is momentum the product of, I should say? Momentum is the product of mass times velocity. It's represented with a lowercase p, and that equals mv. The P, in case you're wondering why it's a P, maybe this help you remember, stood for anybody? I said it last year in class. That was density. That was density. Lowercase p stood for what? Leibniz termed this point, or coined this term. What did you say? Plumpness? No, not plumpness. It stood for progress. So Leibniz came up, think about it. Momentum. It's how much progress you're making. If you've got mass and you've got velocity, you're making progress. Have you ever been doing work and you're like, you're getting through your homework, right? It's the weekend, you're doing a lot of work, and you've got a good momentum going, you feel like you're in the flow. Have you ever said that to yourself? Like, I'm in a good flow right now. Like, I'm really doing good work, and I'm continuously doing, momentum. You're moving. Momentum. Yes, exactly what you should be doing. So momentum is mass times velocity here. Now, where does this play a role? Where does this play a role? What is velocity really when we think about derivatives, or what can we do when we consider this derivative here? What else can we say? The derivative of kinetic energy. It is actually. I never thought of it that way. It's really good, yeah. So kinetic energy in this, right, is 1/2 mv squared. If you take the derivative as a function of velocity, right? If you take the derivative ddv of this, it would become mv. Yeah, it's a really good point. I never even thought about that one. That's not one that's really talked about. Good point, Chip. What else? There's one more. Good, really good connection, Chip. What else?
Derivative changing position.
Changing position as a function of time. So you can think of this as p is also considered to be m times dx dt. Agree with that? And that's with time. So Chip did the derivative with respect to velocity, ddv. I'm doing ddt over here. Yeah?
It's like MA, but...
It is like MA, but give me more.
A, so it would be dA over dt, right? Or is we integrate it?
Good.
So it's integrate.
Yeah.
Integral of, I guess, would be delta V over delta T.
No, sorry. So the integral...
It's the integral of acceleration, right?
It is the integral of acceleration. Good. Which comes from what, though?
A equals delta V over delta T.
Good.
Or F equals MA.
Good. Yeah. So let's relate this to F equals ma is what I wanted to say. So let's relate to F equals ma. And let's think about that for a second. A, by definition, is really dv dt. Does everybody agree with that? Right? A is dv dt. So what else can we do? We can move this up. We could say F dt equals m dv. And then I can integrate both sides. And the integral of m dv, m is a constant, right? It's not my integration, it's not my variable of integration. M is a constant, so m comes out in front. The force is also a constant, or not, I shouldn't say that actually. The force is not a constant here. The force could be a function. Could be a function of time. But m is definitely a constant here. Well, for the AP exam, mass is not going to be changing as an object is moving. Should I say that right away? Let me hold off on that thought for a second. For now, we'll say it's a constant. But the integral of dv is v. And this is going to be v from the initial spot. Let's see. And this is going to be the integral of f dt, which makes this m times v minus v0 equals f dt. This means what? What does this mean down here? M times v minus v0. M times delta v. M times delta v. So Chris, I saw your hand, Chris. So Chris, could you tell me if it's m times delta v, what is that really? The change in progress. Good. Very good. So this leads us into 9-4. So the concept here of momentum being mv, right? Then we go through this whole process and show that, well, you know what? The change in momentum is equal to this. What is this? From last year. Both classes talked about it. But me and Mr. Donachik, I know you both talked about this concept. There's a concept that this is here. Some of you are not seeing it because it really is written as F times delta T in the past. It was F times delta T equals delta T. What is it? Impulse. Impulse. Remember the momentum impulse theory? The momentum impulse theory last year told us, well, you know what? If this F is a constant, we had this last year. F is not going to be a constant anymore. So we're going to go back to this one in a moment. That's really the one we're going to look at that is circled. But last year you had this, and then it was this. Which told us this, which in the very end became this. And this was last year's class that you learned at the bottom. F times delta T equals delta P. But really, the force felt on an object is not always going to be a constant. So, you know, what we do instead is we use what's circled up top there. The integral of force with respect to time is going to equal the change in an object's momentum. Is this on your form of the sheet?
Probably not.
Can we check? You should have it saved, right? In Notability, maybe? And that's just in the beginning of the year. Save that form of the sheet so you've got it in front of you. Somebody check and see, please, if what's circled or what's boxed, if either of them are on your form of the sheet. I think one of them is. I forget which one, whether the integral is or not. I assume the integral would be, because it is calculus form of the sheet, but
It would be lowercase p.
it would be a lowercase p.
Momentum's on the p impulse. It says it's on the J equals integral of f respected dc equal.
Where is that? On the top, bottom?
It's the sixth one.
Oh, it's all the way up here.
Yeah.
There it is. Okay. J is impulse. J is listed as impulse on your form of the sheet. So look for J equals this, which equals delta P. That's on your form of the sheet. It's toward the top. Okay, so it's given. So you don't have to put it in your calculator. But you know what? What does this tell us? If the change in momentum equals the integral What kind of a problem are you going to be looking at? Multiple choice wise. What do you think?
A graph.
A graph. Thank you, Spence. What else?
Another graph of like different variables to then get there.
Okay. More than just a graph then? A graph or a equation or function. Very good. Most likely, when it comes to the momentum impulse theory on multiple choice, you should be ready to be able to read a graph and look for the what under the curve. Look for the area under the curve to calculate the impulse. And once you have the impulse, you'll know the change in momentum. So if you have the initial momentum, or if you have the final momentum, you can calculate the other of the two if you have the overall impulse felt, which is the area under the F versus T graph. Okay, the area of the F versus T graph. What else? How about this last statement? Let's write down. So those are the really big statements right there so far. Let's write down one more statement here. I'm going to go to the next slide. Let's jot down this fact that we could say that if P is equal to mv, then F is going to equal the derivative of P, which equals the derivative of mv, which is really ma. The key is boxed in, the important part is boxed in red here, but just to show you why this is true. F is equal to the derivative of your progress or of your momentum, and your momentum is mv. The derivative of mv, m is a constant, it comes out in front. The derivative of v is a, so you get ma. This comes back to, again, F equals ma. This is really, again, F equals ma. So technically speaking, you could be given a graph of P versus T, where this is not power, but momentum. And I might be able to tell because the units would say kilograms times meters per second. What would the units of power say? Power is the y-axis, really. What would it be? Watts. Okay, so if we see P, we know either it's momentum or power. Obviously, if it's lowercase, it's obvious, but it may not look like a lowercase. It may look like an uppercase depending upon a graph. So use your units to help you to recognize what it is. Most likely the problem will say the momentum of a function of a particle is plotted as a function of time. So you'll know it's momentum. So as a result, if you were given this kind of a problem, okay, something like that, you could be asked many different types of questions. When is the force felt on this object positive? When is the force felt on this object positive? When in these regions? Chris, tell me, starting here. Is it positive here?
Yeah.
Until when, Chris? Tell me when to stop.
Until there.
Okay, then what's the force from this point on?
Zero.
Zero force, because what is he taking? He's looking at the what of the graph? The derivative, which is really the slope. Slope. Derivative is slope. Derivative is slope. So the derivative is positive, the derivative is zero, then the derivative is?
Negative.
Until it gets to?
There.
And then the derivative is?
Zero and this changes to
Positive,
positive.
then negative, then zero, then kind of positive at the end. Ish. I like that. Last thing to leave you with, that's the graph of that one. The other graph that we're going to again be focused on is going to be this one right here. Okay, and from this one, what can we determine? We can, instead of finding slope at any given point, like we did here, slope, 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 we did all those slopes. Here we can find the area under the curve. And the area under the curve there of F versus T, that area will give me the change in momentum of an object. Those are the two things we really want to consider when it comes to the additional calculus portion of this part of physics. 9.3 and 9.4. Okay, so here's what I'm going to do. I'm going to give you some homework. I have the assignment written already. I was locked out of Moodle over break and I changed my password. So I changed it already this morning. We're fine. So give me like 10 minutes. I'll put the homework up on Moodle so you can see it. It'll be homework from 9.1, 9.2, and 9.3. Okay, listed partially. You should be reading. Part of it multiple choice. Part of it homework assignments. And I'll put the problem set up for that. They're all written, but I'll put them all up. So it'll be 9.1, 9.3, and 9.4. I don't give you homework assignments from 9.2. Okay, I didn't give you one from 9.2. My recommendation is that you read page 223 from 9.2. Left side there, we're talking about the fact that if we have momentum as a function of time, force is the derivative of that. Force is the derivative, or the force felt is the derivative of that. So what might we say in this region here? Yesterday we spoke about the different values, but what might we call this region right here? What might we call it when it comes to forces? Have I made a better wording? Yeah.
0 at that point.
Yeah, so what do we use? What's the phrase we say when there's no net force? We say the object is in, what is it? Yeah, equilibrium in this region. So either it's not moving in this region, or it's moving with a constant velocity, constantly. So keep that in mind that, you know what? The momentum is constant, and so is the velocity constant, right? Think about that. That makes so much sense. Momentum is mass times velocity. So if the momentum doesn't change, the velocity can't change. Again, if the momentum doesn't change, the velocity is not changing. We are making an assumption that the mass is constant for all of these problems. By the way, I like the white. I just thought I mentioned it. I really do. I saw that yesterday. I know it's different, right? This year's is different.
I like it.
It's really nice.
I didn't like it at first.
A lot of people don't
Oh.
like it. I really like it. I feel like it ties this.
I saw it today, and I told Myers that maybe we should keep it going on next year, too. I like it a lot. Because she said to me, she goes, oh, no, it's a headache, it's a headache. I go, it's a headache? What? She goes, we didn't mean to get those. And I'm like, really? She goes, yeah. I'm like, actually, I like them a lot. I saw Alex had it on earlier. That's why. It's really nice. Anyway, so yeah, the constant velocity in this region is because it's a constant momentum, but you could also recognize if it's a constant momentum, the force is 0, and if the net force is 0, there cannot be acceleration. And that's why this is also considered constant velocity. So there are so many connections between all of the laws that we're learning, and that's what I want you to recognize here with these two graphs. So let's get a look at an example now. So let's look at example, let's see, what page was it on? This is 9.4 that we're going to focus on. 9.3 is just the introduction to what momentum is, and then 9.4 applies the momentum impulse theory. So let's look at the example on page, where are we? Page 229. Okay, let's look at page 229. So here's what page 229 says. It gives us a figure, and it shows an overhead view of a path taken by a race car driver as his car collides with a wall. So here's what the image looks like. This is the wall. Here's the driver. The driver's about to hit the wall at an angle of 30 degrees. The driver rebounds off the wall at an angle of 10 degrees. Let's see, anything else given? Anything else given? No, that's all we're given for the diagram. Okay, so this is the driver hitting. The impact occurs. And the impact occurs, we'll put a little X there maybe so we know what we're talking about. It occurs at that X, that location. And then the car comes careening off the wall. By the way, if anyone sees NASCAR, there's a huge accident recently. Anyone see that? That was crazy. The guy's okay.
Yeah.
Like, completely okay. Walked out of the hospital like 3-4 days later. Like, no problems at all. Really amazing, actually, what they do with NASCAR cars, the way that they design them. There's a whole thing about how they design the cars to absorb all of that extra energy that you have. And it's really incredible, actually, the whole structure of the inside of a car now, or a NASCAR car. Anyway, so this car collides with the wall, rebounds. It says just before the collision, the driver is driving with a speed of 70 meters per second. And then just after the collision, the speed is 50 meters per second. The question says, the mass... let's see. His mass. So we're looking at the person inside of the car and the impulse felt by that person. The person's mass is 80 kilograms.
And that's like the initial defined word.
Correct. Yep. And that's what we're going to talk about right now. So this entire topic, this entire section is about conservation, really. And we haven't even gotten to 9.5, which is all about conservation. But because you took this course last year, conservation momentum carries forward from conservation of energy. Now, we're not looking at conservation yet. We're looking at the impulse felt. So the question says, determine the impulse felt by or on the driver. Now, when we look at this problem, at first it looks like, oh, this isn't that bad. Right? We've got a change of velocity. So a change of velocity. We got the mass. We can find the impulse. What's the problem? What makes this a difficult problem suddenly? There's one thing that makes this a difficult problem.
Change
The change in the angle. Very good, Chris. If I were to do this, ready? I were to run forward, and then just run into the wall. Like, that'd be ridiculous, but I'd be running into a wall. My velocity would go from 4 meters per second to 0. And I would have a change in momentum, and I could find the impulse delivered by the wall. And that's an easy problem. mv minus mv, see the change in the momentum? That is the impulse. I'm done. The problem here is that the momentum is occurring in 2 directions. And we're going to start talking more about this. Last year, you probably worked only with one-dimensional momentum, which is, I know what I did, and I think you as well did. It was always linear, but it was one-dimensional linear. Now we're at 2-dimensional. So let's take a look at this problem and dissect it a bit more. So if we look at it first, if we look at the object in the beginning, we want to break up that beginning momentum into 2 pieces. And then we want to break up the final momentum into 2 pieces. And then find the difference in those specific directions, the x alone and the y alone. So let's go ahead and do that so we can show it. So here's how I look at these problems. And you don't have to do it the same way. You don't have to even write these words. But sometimes I think of before and after. Okay, which is really just initial and final, right? Before and after. The reason I'm using before and after is because with these problems, what always seems to occur? With momentum problems, there's always a change, but in general, there's a collision or explosion. So there's always a before and after where the particles are acting differently before something happens and then afterward. Similar to conservation of energy, where it was like, the beginning of the problem and the end of the problem. 2 different instances in time. And that's the same concept here, looking at 2 different instances in time, but specifically separated by a collision. When the collision occurs, that's the before and the after. Or when the explosion occurs, before and the after. So before the collision, we've got x momentum and we've got y momentum. And then after, we've got x and we've got y as well. And remember, momentum is mass times velocity. So this is going to be m times v. What do I write for this one?
Cosine.
Yeah, this is going to be cosine of theta in this case. And we'll put theta 1 for now. And then in the y direction, it's going to be mv times the sine of that angle. So yes, we've got here 80 times 70 times cos 30. And this is 80 times 70 times sine 30. So what am I doing? I'm finding the x component of the momentum by doing mv cos theta, and then the y component of the momentum by doing mv sine theta. I'm doing this because I want to see how much the momentum has changed in each direction from before to after, but independently in each direction. I want to look at the x and I want to look at the y direction. So afterward in the x direction, the velocity is now what? Or the momentum is now what? mv. I'm going to put cosine theta 2 for now, which is going to be 80. His mass is still constant. The velocity is 50, and the angle is now 10. Be careful with the last part here, please. Please be very careful with part 4, whatever you call this. I'm giving you a hint by saying that, obviously, right? By saying be careful. There's clearly something about this last part. I want you to realize it. I saw 2 light bulbs click. Right? You both just went, oh, that's what it is. Do others see why I'm saying be careful? What's the difference in this 4th part compared to the other 3 parts? What's the major difference that's going to happen here? Same 2? Anybody else? I saw you both recognize it. What's the main difference in this last part? You got it?
Because it's going down.
Yeah. It's going down. So the y direction's momentum is going to be negative after the collision. That's a huge deal. Because now when I do final minus initial, I'm going to see that it's going to change my answer. Okay? So this is going to be mv sine theta 2, but v is negative in this part. So it's going to be 80 times negative 50 times the sine of 10 degrees. And if you want to put the negative in the front, you can. I'm just putting it next to the 50 to make it look like that's the velocity. That's negative there because it's going down. Downward is negative for velocity. All right, so these are important values. We're going to need all 4 of them. I think I've got them written down here in this problem, so I don't have to worry about it much. No, I don't have them written down. They just give me the change, not the actual value. So what is the before and after in the x? What do we get for numbers? Anyone have numbers for me for the x or the y? What do you got, Chip? Give me something.
For before on the x, I got 4,849.7, and then for the after, I got 3,939.2.
And what are my units for momentum? Anybody remember?
Isn't it kilograms meters per second?
Yeah, that's it. There's no simplified unit. One of the few times we're going to see this happening. Okay, everything is in base units. Interesting, right? How has nobody termed that, right? How has no one said, let's call this a Leibniz? Leibniz is the mathematician that came up with progress. He and Newton were kind of going back and forth. If you talk about Leibniz in calculus school, he and Newton discovered calculus pretty much at the same time. So they just had different notations. So you hear Newton notation, Leibniz notation. Anyway, he was the one who coined the term progress, which is where P comes from momentum. Yet nobody thought to give this a summarized unit. Like the joule is a made-up unit. Somebody just said, you know what? It was probably a guy with the last name of Joule. It's usually where it happens, like Ohm was after Ohms, Newton after Newton. But nobody coined a term for this unit. So this is just kilogram meter per second. Okay. What's the change there? Final minus initial. Final minus initial is at negative 910 approximately, or 910.5. What does that come out to be? What's the exact value?
Yeah, it's a negative 910.5.
0.5, okay. The book just writes 910. I thought there was a 0.5 in there. All right.
Sometimes I've seen it written as for the unit like NS.
Yes, because if you simplify what a Newton is, it cancels out to this. So you could have, it's Newton times second, not divided by, yeah. You could write, you hear what Kara said? Newton times second is the exact same unit as this. How do you know that for sure? Well, that's impulse. Impulse is F times T, isn't it? F is newtons, T is seconds, and impulse equals change in momentum. So Newton times second has to be the same unit as kilogram meter per second. You could show that by recognizing that Newton is really kilogram meter per second squared, and then times the second cancels. Okay, so you could derive where that comes from. Yeah, good point, Kara. It could be Newton times second. Very good point. Y direction, values in the Y direction. What do we have for numbers real quick? Chip, good.
For before, exactly 2,800, and then after 694.6 kilograms.
And that's negative, right?
Yes.
Okay. So now we do final minus initial, so negative 694 minus 2,800. Now we can see how the negative does play a role here. What do we get? Negative 3494.6. Is that right, Chip?
Yes.
Okay. So let's think about this problem. We've got a change in momentum in the x. We've got a change in momentum in the y. They're not the same value. Again, that's the key here. We're not only moving in one direction, we're moving in multiple directions before and after this collision. So we have to take a look at both of those changes in momentum and think about what they represent. The change in momentum in the x direction is the impulse felt in the x direction. So we could say an impulse, we're using J, is that right in the formula sheet? So we could say that the impulse in the x direction is equal to negative 910.5. And let's write that as Newton's second, just to be, different. Because as Kara said, impulse is force times time, so it makes sense to write that way.
Why did you call it J?
J for impulse. We're using J for impulse. It's just on your formula sheet this year, it's J. It's not capital I, it's J. I stands for moment of inertia, we're going to talk about a little bit later. So we're going to use J for impulse. And then the impulse in the y direction is simply negative 3494.6. And again, I'm going to change my units into newtons times seconds, even though they're the same thing. So these are my two values for my impulse felt. And we want to figure out the overall impulse felt by this driver. So think about being the driver right now, okay? Imagine you're the driver, first of all. Good luck surviving this, because this is a lot of impulse. talk about how much impulse it is at the end. But the driver is not only hitting the wall and getting rebounded off the wall, but he's also hitting the wall and it's slowing him down in the x direction. So look at both of our impulses. Both signs are what? Both signs of impulses are both? Yeah, because he's not only slowing down this way, but he's slowed down so much vertically that he or she rebounded off the wall. Right? Think about it. Here's the driver's driving, he hits the wall. It's slowing him down this way, which is the negative impulse in the x you're feeling. But then it's rebounding him off the wall in the y, which is why this is such a large impulse here. The wall is pushing back, changing his direction, which is a huge impulse felt. Here, the x direction, there's no change in direction. He was going to the right and up, and now he's going to the right and down. He's still going to the right. So there's no change in direction in the x, which is why this impulse is not as much. Do you see the logic behind what I'm saying here? Much larger value because you're getting rebounded off of a wall. The key, though, is to figure out what the overall impulse is felt by the driver. And if the driver feels these two impulses, and they're vector quantities, remember J is a vector, just like V is a vector, which is why in your formula sheet you saw this. Right? That's your formula sheet tells you. Impulse is change in momentum. Impulse is a vector quantity. So we have to recognize that the impulse felt here is felt in the x and the y direction. So we have to think about overall, this driver, let's think about the driver as being like right here, that dot. This driver is feeling an impulse this way and an impulse this way, both. So which way is the driver feeling the impulse really? He's really feeling the impulse in that direction in blue. So this is like, it's not, but it's like a diagram, right? The force felt by the wall pushing back, slowing him down in the x, is going to push back. So here's the driver again, right? Here's the driver, hits the wall. The wall's going to cause friction to push him back this way. It's also going to push him down this way. That's these two vectors here. So the overall impulse felt by this driver is shown in blue. He's feeling a combination of both the x and y impulse. So how could we figure out that length in blue? How could I figure it out? Yeah, it's just Pythagorean theorem. Jx and Jy. Okay, we're looking for the overall magnitude or the overall value of the impulse itself. And we could figure out the angle as well. So squaring those two and square rooting, I'm going to give you an approximation. It's 3616 approximately. Approximately 3616. Okay, approximately 3616. More than either of the two, obviously, because it's not obvious we're getting. Pretty close to the y value because it's such a large number. It kind of outweighs the 910. And because it's impulse, technically there's an angle as well, so we could find the angle. Okay, how can we find the angle? Well, we could look and say, well, this is the angle here, theta. Let's call that theta right there. So then the tangent of theta equals y over x. So to get theta, we could do the tangent inverse of jy over jx. That theta is going to become 75.4. But that angle, remember, is measured in this diagram. So if we're talking about an angle 75.4 and that's here, if I'm looking at like the unit circle, you might be given a value of like, I don't know, 255.4 because it's 180 plus another 75.4 right here. Again, we're getting this angle that's kind of wedged in here. But if we're running the angle with respect to the initial axis, the initial direction, well, it's not the initial direction actually, it's just the angle backward, yeah. It's not the initial direction. But that's the impulse that's going to be felt. So why is this important? This kind of a collision will happen. What does the book give as a number? What is it? 14 milliseconds this will happen in. 14 milliseconds. That's how long it will be in contact with the wall for. So let's think about this for a second. Again, the driver, right? Oops. The driver is in contact with the wall for 14 milliseconds, which is really, milli is 10 to the negative third. So I got to move the decimal 3 spots to the left. So 0.014 seconds. That's the time period we're looking at here. And that is reasonable, actually. For a car collision, it's happening like that, right? Clearly far less than a second. What can we deduce from the time given now? What else can we figure out? The book is going to ask you for it, but before I even get to the question, you guys tell me. If I know the time period of the collision and I know the impulse felt, what else can we then find? We know time and we know impulse. What else can we find? What else? Chris? The force. The force felt. So remember that impulse is really force times time. Now, if it's a variable force, we've been saying it's the integral, but what we're going to find out right now is the average force. Okay? We're going to find the average force from this. Sure, the force felt on the driver might be really, really little, and then spike up, and then drop off. And we saw that curve, if you recall. It's in your textbook, actually, on page 227. It's this image. I'll put it in the top right. Okay? This is what it is. Usually, that's a impulse curve. This is force, and that is time. Because traditionally, upon a collision, the force is not felt evenly the entire time. You hit the wall starts slowing you down, and then you feel that spike, that largest force you feel, and then that force will drop off. So you're not always going to feel an actual value for a certain time. Sometimes these kinds of graphs will be approximated like this. I use red. That's what sometimes these graphs will look like. And they'll approximate that what looks like almost a normal curve at the top into what we would consider a step function. It's a step function where it's like nothing, 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 and then it's a step, and then it's back down, and then it's a step, and then it's back down. Now, either way, in this case, we're still finding the area under the curve when we find J. Right? J is the area under the curve. So if we know the time period, this delta, we could say, all right, well, you know what? Let's divide by t, take J divided by time, and we get the average force. So that will give us whatever this force is here. It will not give us the max force at the top, because that's assuming the force is a variable function. What I'm saying is that we're looking at an average force felt on the driver during the whole time. So we're really focused on something like this right now. Okay, like this. And this is where, what theorem have you guys learned in calculus? That takes a function that is a variable function and allows you to figure out the general value throughout. There's a theorem in calculus.
Question, do you know the generic password to get into the computers if you don't know?
Yes, I think I have it before. Oh, you the kids?
Yeah.
Oh, new heights, no caps.
That's it.
All one word, no caps, new heights, new heights. Both user and password, yep. No problem. You figured it out? Chip's gonna send it?
Isn't it the first fundamental theorem?
First fundamental theorem helps us with it, yes. But there is a theorem that you guys have learned. We talked about it. On the right back from Camden. Come on, man. Who's that memory? On the right back from Camden. Who were you in the car? Was you and Matt? No. Was it Matt?
Yeah. Yeah. What were we talking about though? I
What
remember.
are we doing here?
I remember.
A function that may vary, and we want to get an idea of what the function is in general. You find the
Oh, the average. Yeah.
average
the
value
average
theorem. Remember the average value theorem in calc? You guys have learned it.
Yes.
It's when a function keeps changing in
It's
height.
like 1 over b minus a integral a to b. Yeah.
Oh yeah, now that you know the formula that makes sense. You gotta know what it actually is. That's what this is right here. So look at the function up top. The function up top clearly is a variable force, right? It goes up, it drops back down, it teeters off. This is an average value function of what you're seeing up top. It's figuring out what is the average height of that function, which is what 1 over b minus a times the integral of a to b of that whole thing, right? That's what it is, but that's what we're figuring out here. So we're finding the average value. So let's take J, 3616, and let's divide it by time, which is 0.014. What does that force come out to be approximately? Anyone got a number for me yet? What is it approximately? Yeah.
757,946.
That right there?
Fraction.
Yeah.
757.
No. 257.
257. Got it.
257. Yeah, that would hurt.
257, 947 newtons. 257, 947 newtons. Now, let's see. Your mass is 80 kilograms, right? Okay, your mass is 80 kilograms. Divide by 80. When you divide force divided by mass, what do you get? What's the acceleration, Chip?
3,224.
Divide that by 9.8, Chip.
329 G's.
329 G's. Do you know when you pass out after? How many is it?
50 or
It's far less.
5.
It's like 5 or 6 G's.
something. Oh.
After like 5 or 6 G's, your body's just not going to respond. You're going to pass out because what will happen is your blood rushes to extremities.
So is that why people sometimes like lose consciousness?
Yep.
Outside
When
of-
they go in the roller coaster and they pass out in the loop on the bottom, and then they wake back up and then they pass back out and they keep waiting. Have you seen these videos?
Yeah.
Oh, they're hysterical. It's not fun. They're so funny because people don't even know what's happening as they're doing it. They're just passing out, and then they wake up and they don't know where they are, and then they hit another loop where the G factor goes up, and then they pass out again. Anyway, so yes, this would be 329 G's. So you would not survive this crash. Okay, so now, what do mechanical engineers do to help survive this crash? No, not just what did they do, but for this. Yeah.
They make it so like the front part of the car, like where the engine is, crumples when you hit something, so the time is increased, and so the impulses.
Which is the same thing that gymnasts do. When gymnasts dismount, how do they land? Does anyone ever land like this? Try it. It hurts. Seriously. If you want it, you stand on a chair, just the chair, not the desk, the chair. Jump off and lock your knees and land. You'll feel it in your teeth. That's how much it hurts. Seriously. Your whole body. So what do? Yeah, bend your knees when you land. It's the same concept with anything. Anytime you want to absorb impact, baseball players know that. You catch a ball barehanded, what do? Soft hands, right? Egg toss. You guys egg toss before? Black parties egg toss, right? You cradle it. You cradle the egg as you catch it. Anyway, the concept is that the engineers, yes, they allow the front part of the car to crumple. What else do they do? Or what else have we done over the last 40 years? What do we use now? Airbags. Airbags are deployed upon a collision. An airbag is deployed when it senses a change in the velocity of the car that's dramatic enough. When that change in velocity occurs in a small enough time period, it's electronic obviously now, the airbag, boom, pops out. It used to be what? Anybody know how airbags used to work? When they were just invented, like in the very beginning? You had to actually hit the dashboard and a force would cause it to pop out. Is that really useful to me? Not really, right? So when airbags started, it helped. It definitely helped because it still pushed you back. So people would hit the dashboard, right? It would break their face. They would crumple into the dashboard, maybe go like through a windshield. So the airbag at least pushed you back a little bit. But it took you hitting the dashboard for the car to recognize there's a force felt over a small time period, a high impulse, and as a result it would respond. Now,
Fiberglass for a while.
Say again?
Did they make cars out of like fiberglass for a while and it would just shred? Yeah.
like the body of it, the frame.
Oh, yes.
Fiberglass?
They made out of fiberglass and they would just shred when they crashed.
Like it would literally get cut in half kind of
They
thing?
would like the fiberglass would splinter and it would just like
Ooh, like a grenade almost. Like
Yeah.
shrapnel going into
Yeah.
your body everywhere.
Fiberglass splinters are the worst.
I've never had a fiberglass splinter, I gotta be
I
honest.
have a septic tank in my backyard where I go in the summer, and we used to like lay on it when we were little. Because it's like, I don't know, it looks like a hot tub, but it's not a septic tank above ground.
Yeah.
So we lay on it, and then we get fiberglass splinters all over.
No way.
that's
Yeah.
really
That's really.
I wonder how that is in your body. Fiberglass, like splinters.
I don't know.
Weird, what's all that do? All right, yeah, but anyway, a ton of force, right? So they increase with airbags. It's all about increasing the time of the collision. Because what can't you change here? What can't you change? You can't change the force. The force is the same force. So if you increase the time, it'll decrease the force. You follow what I'm saying here? But you physically can't just be like, oh, it's less force suddenly for no reason if you have the same time period, because the impulse is a constant. If the impulse is a constant, there's no way that you could just suddenly change the force unless you change the time period itself. Okay, keep that in mind. They balance each other out. If force goes up, time period goes down, and vice versa, assuming impulse is constant, which it is. The impulse is the change in your momentum. And if you're going from 80 miles an hour to 0, no matter how you do it, the change in momentum is the same change in momentum. Okay? It's about the time and the force felt that matters. All right, can we move on to 9.5? Let's move on to 9.5. And 9.5 is going to involve 9.3 and 9.4. I'm going to pause.